So here we're going to do an example, finding the critical numbers so we can determine the increasing and decreasing intervals for this function. So the one thing we know is that the critical numbers occur where the derivative is equal to 0. So I'm going to go ahead and find my derivative here, and when I'm looking at this, x times e to the negative 2x, that is a product. So we have to use our product rule, and with our product rule we have a first and a second, or a first and a last. And so remember, the derivative with respect to x of first times last, or you could say times second, is going to be to first times the derivative of the second plus second times the derivative of the first. So in this situation we have x times the derivative with respect to x of e to the negative 2x, so we're going to need to calculate that, plus e to the negative 2x times the derivative with respect to x of x. Okay, so I have two small derivatives to do here. Let's see, I've got f prime of x equals x. So when I take my derivative of e to the negative 2x, the derivative of e to the x is e to the x. So this becomes e to the negative 2x. But because that argument we have in our exponent right here, because that is more than x, we have to apply the chain rule. So that means we would need to multiply by the derivative of the inside, or the derivative of what is inside the exponent in this situation. And the derivative of negative 2x is negative 2. So then I have plus e to the negative 2x, and this derivative of x just becomes 1, which we don't need to write. So cleaning this up, f prime of x equals negative 2x e to the negative 2x plus e to the negative 2x. And now we're essentially done taking our derivative. But when I'm dealing with derivatives, I always like to make sure they are in factored form, because that's going to help me when I need to solve it equal to 0. So technically at this point, you can stop. But, you know, again, we like that derivative to be as factored as we can make it. So one thing I notice is that both of my two terms, they both have an e to the 2x in them. So I'm going to factor that GCF out. So if I factor out e to the negative 2x, so that's my common factor, what am I left with for each of my two terms? Well, the first term, if I factor out e to the negative 2x, I've got negative 2x, plus the second one, if I factor out e to the negative 2x, I have nothing left. But there's essentially, I need that little placeholder, an invisible 1. Okay? So personally, I think this is a better form for us to state our derivative, but the line above it was okay for the derivative. Okay? So we found our derivative. We need to set this equal to 0 in order to find our critical numbers. So 0 is e to the negative 2x times negative 2x plus 1. And because this is already in factored form, if I'm multiplying two factors to be equal to 0, then I know each one of them needs to be equal to 0. So e to the negative 2x equals 0, and negative 2x plus 1 equals 0. In this situation, I can solve each of these. The one on the right is pretty easy. It's linear. I'll subtract 1, divide by negative 2, and I get x equals 1/2. On the left, we're solving an exponential equation. And solving that exponential equation means we would take the log of both sides, or convert this to a logarithm. So when I take the natural log of both sides, on the left it's going to cancel that e out, and I've got negative 2x, and on the right I get natural log of 0, which of course we can't take the natural log of 0 because natural log is not defined there, so there's no critical number there. So we just have one critical number. And of course, sometimes we get a second critical number solving this other piece of the equation, but in this case, we ended up with an undefined value. So at the critical number, that means a max or a min will occur there. So what we do is we take our critical number, and sometimes we have endpoints of a domain, like if we had been given, oh, this is between 0 and 10, we may have that. But in this case, we're not given a restriction on the domain. It's just for all numbers. So we only have the 1/2 to consider, and we choose a number on either side of 1/2 to test. We can choose any number we want. I'm going to try and choose the easiest numbers, x equals 0 and x equals 1. Those are my test values. And I want to test them in the first derivative. And so my first derivative here is e to the negative 2x times negative 2x plus 1. So testing them in the first derivative, I'm going to be looking to see if I get a positive or a negative value. The derivative tells us the slope of the tangent line. A positive slope would mean the graph is increasing there, and a negative slope would mean the graph is decreasing. So when I test x equals 0, f prime of 0 is e to the negative 2 times 0. That's just e to the 0. And negative 2x, or negative 2 times 0 plus 1. So e to the 0 is 1. Negative 2 times 0 plus 1 is 1. And 1 times 1 equals a positive value here. So what we know is that f prime of x, any value I'd choose, would be positive. And positive to us is going to indicate that the graph is increasing. So we'll do the same thing, f prime of 1. F prime of 1, that is e to the negative 2 times 1 times negative 2 times 1 plus 1. So negative 2 times 1 is negative 2 plus 1. I get a negative 1 here. And that is 1 over e squared. So I've got essentially negative 1 over e squared, which is a negative value. F prime of x, my derivative is negative on this part of the interval. So that means it is decreasing. Okay? So now that looks a little messy because of my scratch work. So I'm going to rewrite that here, what we were looking at. We said that for our graph, we knew there was a critical number at 1/2, and that the derivative for any x value on this interval from negative infinity to 1/2, that's an x interval, we said that the derivative was positive. So if the derivative's positive, that means the graph is increasing on that interval. And from 1/2 to positive infinity, if we test values in the derivative, we get a negative value. A negative value means that it is decreasing. All right? So because it is increasing and then decreasing, we know that the graph goes up and then back down. And so this is a little bit of forward-thinking knowledge, but because the graph was increasing and then now it is decreasing, it went up and then it had to turn around, we know that there's a max at x equals 1/2. Okay? So it was going up and then going down. So possible answers to this question might be that the graph is increasing, when x is an element of the set, or x is on the interval from negative infinity to 1/2. We are decreasing when x is from 1/2 to positive infinity, close that, and the max is f of 1/2 at x equals positive 1/2. And so I wrote f of 1/2 because I don't have that value here, but always remember the max is y, it occurs at x. And if I want to find f of 1/2, this value would be found by putting 1/2 in the original function, not the derivative, okay? So that's how I could find what that number would be.